Okay, hello everyone. Today I'm going to talk about running big data pipelines in production. So basically, we're just gonna kind of walk through some of the pitfalls and what's happening sometimes when you need to run the pipelines and what can kind of break in the process. So I'm Roksolana. I work as engineering manager at Captify. Captify is a UK-based edtech company with the office actually just around the corner in Covent Garden. So we have multiple teams running Scala and big data pipelines, and like the company has been in the market for 12 years, and most of the pipelines since then were built in Scala. Also, I'm part of the Women Who Code Kyiv community. I'm one of the leads there, and I often speak at meetups and conferences. So first of all, a little bit about tech domain. So ad tech is basically advertising on steroids. So usually, like in the past, you could see the ads on TV, and now you can have kind of more tailored to the audience's ads. So as a consumer, we can see the content, which is kind of, we have recommendations and ads that are tailored to us. So basically, kind of two sides win. The side of the consumer is basically getting the stuff that we are interested in, and for advertisers to basically sell their stuff to the consumers which will be actually interested in that. So kind of finding this link between consumers and advertisers. So in terms of tech stack, we use a bunch of storage systems, which is Google Cloud, Amazon S3, and HDFS. The pipelines are built via Spark, Kafka, and Flink. And we are running some pipelines via Databricks now and kind of transitioning from Impala. So I'll tell more about the transition in the process. So basically, kind of the main idea of the talk is that people often talk that how to build a pipeline, what were the steps to build that, but you can't always hear the stories of kind of what actually happens after that in production. And the thing is that pipelines are not static. Like there are changes over time, some evolution, some framework changes and technologies, and basically errors in production. So my talk is kind of about that part of programming when you actually have pipelines already, but that's like the kind of stories that happen with them. So first of all, types of issues that happen, the most common one is low performance, especially with Spark. So basically we have some expectation of how long the job is supposed to run, and we see that the performance started to decline, or overall we couldn't, for example, expect some data load, and that's why our pipelines don't work basically as good as we expected. The second one is data source errors. Those are kind of the easiest to catch. Basically, the data providers or wherever we get the data stopped delivering the data or change the format of the data. So it could be a bit tricky if the pipeline is quite complex to kind of catch that. But overall, those are kind of the easiest to fix because basically the issue is on the other side. So it's always like more pleasant for developers to say that that's not our issue. Someone can fix it there. Human errors could be tricky as well. So like running the wrong query, using another environment that was supposed to use, like QA versus production. Those are kind of simple on the side, but actually harder to prevent in a way because there is always like a gap for the moment when someone just makes this kind of mistakes. So yeah, oh well, all of this stuff happens all the time. So first story that I'm going to tell is called Unlucky Query, which is basically about human errors and the kind of queries that developers can run in their own environment in their own time. So what happened in that case is that someone just dropped 13 months of data on a production environment and via a SQL query. That happened like because of many reasons. And first of all, that like permissions set up wrong in a way that anyone like could able to do that. So basically this data was a bunch of so-called user profiles. So in advertising, it's kind of defining the user in terms of different demographical data, like for example, gender, age, some location. So that's like user profile. And this is not like the most critical pipeline, but it's still quite widely used by different teams. So the way that pipeline is built is that we grab some data from HDFS, we have a Spark job, deliver the data in Parquet format to another HDFS, which is basically kind of the background behind Impala. So Impala is a query engine, which is built on top of HDFS. So for the users, it looks like there is like simple SQL querying, while in reality, we just basically move the files from one HDFS to another, and by defining kind of the structure of the table, they are able to query it via SQL. So what happened there is that the users don't see the data in this part, with kind of querying the data, and that's where basically it was dropped. So, but we actually still have the data in our source. So another team is delivering the data in the format of kind of on the hourly basis, and we don't have it just in the end of the pipeline where when we deliver this data to Impala. So yeah, that's the kind of thing you want to do, kind of a revert, because 13 months is quite a long period. And in this case, the good thing is that the amount of data is not actually huge, because the feed itself is not huge. It's not like terabytes of data, so it's basically revertible, but it still kind of takes time. So what we had is a loading mechanism, which allows to kind of take the period from now back in time, which was usually 5 days. So we process the data over this kind of 5 days, and then we just deliver it in the end for the users to see. What we could do, like a simple state here, is just define the certain months and kind of get this data back. But the issue is that Spark job kind of is not able to process that much data in one run, and basically there is a risk that it's going to fail in some of the stages, and we're going to have like corrupted data or partially processed data, which is even worse than not having the data. So we decided to kind of take the safer approach by pushing month by month. In some cases, like for example, newer data was a bit more heavy because the data grows over time. So for like newest months, it took a bit more time. But for older data, we could process just a bunch of months in one go. So it was quite easy. Plus, it was a good kind of approach because the users usually need only 1 month of recent data for daily reporting, and kind of a year of data they need only once a year when they do this final like revenue reporting and stuff. So that's why just giving them back this month kind of saved the day, and then we could like step by step upload all the next months. So it worked out well in the end. The next story is called missing data. So I think it's kind of a typical thing in big data processing when at some point of the pipeline your data disappears and you need to figure out what actually happened there. So kind of detective story in a way. So what we have is a pipeline which ingests the data from Google Cloud. There are 2 Spark jobs, one extractor, which just extracts the data and pushes it to Amazon S3 in specific partitioning mechanism that it kind of works better for us. Then we have a more kind of heavier part of the pipeline, which is data cost attribution job, which delivers the results to HDFS. So what we have is the data missing kind of in the end of the pipeline. So as you can see, there could be 2 places where it got missing, like in the source, in the extractor job, or in data cost attribution. So what we checked first is the source because it's easiest, and we actually saw that a data provider kind of changed the names of the columns without actually notifying us, and therefore we have missing data. So basically our job is tied to the specific kind of selection of columns because we needed only them for reporting, and basically our job just sees no names of such columns and just does nothing basically. Kind of running without the need to actually run the data because there is no data. So what we need to do simply is sort of rename the columns, but at the same time, we have the issue of having like 1 week or even less than a week of data with new column names and a year of data with the old column names. So doing like reprocessing and renaming of the whole year, that's kind of a huge effort, especially for the users as well. And kind of reloading for 1 week is one thing, but 1 year is like way too much. So what we applied is just a mechanism when we kind of take 2 versions of the data. In case it matches kind of the old name, we just rename it sort of in the code. And in case it doesn't match the old name, we just like put this new name, which is we consider kind of correct or standard in a way. So basically, we do that just in the code. The users don't see the actual source columns. They just see the data with kind of new columns, and it works out well for them because they kind of don't see the whole behind thing. So in the end, we sort of have renamed columns, but in reality, we kind of do this switch for the older data, while for newer data, we just transition to this change, and everything works well from there. The next story is called Divide and Conquer. So basically, some issues could be quite easy to kind of catch and solve, but on smaller scale. So like the issue that I'm going to talk about is kind of not that complicated itself, but because of the scale of the data, it's harder to solve. And that's why it's easier to kind of build the smaller chunks and go from there. That's why basically divide and conquer. So we have some Spark job, which does quite heavy aggregations and filtering, and basically processes some data for a month with partitions in the source based on processing time, and in the end they are just kind of created for the new date. So basically we have snapshot of data for a month. So that's quite a lot of data, and aggregations are quite heavy on Spark. So that's why over time, basically, driver is not able in Spark to process that much data, and we started to think about some changes that we can make. So the job started just to consume lots of resources, even kind of dropping more and more memory to the driver. Increasing number of executors didn't help. The processing became quite slow, even with the increase of resources, which is basically costs more. And in the end, we have large Parquet files because basically we ingest a lot of data and we want to deliver the data for like the whole day, which is quite big Parquet file to work with. And basically that's one of the big data problems often, to have like large files or too small files. So all of that is kind of not good. We have declining performance, costs are increased. Someone has to check the job manually practically every day because there is a chance that it's going to fail and we need to add more resources. So it's nowhere to go from there. So the solution was to generate a so-called seed partition column. Basically, in our feed, we usually use, as it often works, unique potentially unique columns for partitioning. So for example, some IDs, for example, gender data, because there are only two values. So basically the data that has a limited set of values. And in the case of this feed, we were not able to add more columns for that. I mean, like choose from the ones that we have, because it was a URL feed, and URLs are usually quite diverse, same as domains, and they don't repeat as much. And therefore, we use this mechanism of seed partitioning. So basically, you just create a new column by building a hash on top of one or many columns. And that works quite well because in such a way we can control partitioning better and kind of do that more kind of customizable partitioning than relying actually on the partitions that we have. So we kind of wrote the new partition state from there. And we needed to also run the jobs that depend on this one, because there is the whole pipeline with kind of the smaller states. So how it looked in the end is that in the beginning we had this processing time, like huge Parquet files. In the end, instead of having, again, like in created folder or partition, one huge Parquet file, which is kind of one-to-one mapping here, we basically build this one-to-many mapping. So in each of the partitioning folders, we have buckets. It could be like the number is not random. It usually requires a set of kind of experimentations on top of the data to figure out what works best. So it's not like the number is supplied as a magic value. It's more than within the job we specify kind of the formula by which we define this number, and over time, if the data grows, we will kind of have larger partitions in those buckets, or we will basically rebucket. So the issue only for downstream jobs is to read the data properly, because if they were kind of reading the data from created bucket, created a folder, they won't be able to do that via kind of bucketing. So we needed to adjust that as well. But overall, that worked well, and over time, kind of the job started to stop failing, and I think it's been a while since we checked at all what's been happening there, because the job just started to work fine, and we started to apply the same mechanism for other jobs which experienced similar issues. And the next story is called Catch the Evolution Train. So this story is about migrations to different tech stacks, or kind of having this huge idea of what we want to have in the future for engineering team, and we want to kind of jump on that evolution train and deliver that as fast as possible. So basically, I think each of the companies has this kind of visionary person. In the case of kind of my team, mostly like engineering team, there was an architect who defined the vision that we want to switch to kind of data mesh using Delta Lake, and to basically build different layers of the data, because what we had before that is kind of a bit of a mess when some of the feeds allow to get the data like more aggregated formats, some of them allow only raw formats, so for the users it's not like the best approach. So basically the idea of this evolution was that we deliver different types of data sources, batch or streaming, and then we build a kind of layering of those of the data that we get. So first layer is called bronze, because it's usually raw data, just what we get from data provider, maybe in just better format for us, but overall no other like processing or filtering added there. The next one is silver layer, where we can have filtering, some cleanups of the data if necessary. And the last one is gold layer, where basically we have aggregations. So for example, some financial calculations, anything like that. Behind that, we can have any storage systems. It doesn't really matter. The whole idea is that on all of the steps of these transformations, the users have access to the different versions of the same feed. And basically different users kind of have access, because engineers are usually mostly interested in bronze or silver layer data. The kind of final users like analytics, they're interested usually in gold level data or sometimes silver. So kind of this layering helps to see the feed in different stages, and also allows the users to see raw data if that's necessary, and understand what kind of changes went from there, and if the algorithm is the right one. For example, if you work with some kind of teams that work mostly with raw data. So, like how we stumbled upon this problem is that this evolution has been going for a while. A bunch of teams were working on that, and like there was a plan on how we get there, but specifically like my team, we contributed to that. But there were a bunch of feeds that were transitioned to Databricks, and at some point the users realized that they don't see some of the columns that they want to see there. Like they've been using this feed for a while, and now when they want to fully transition, they don't see some of the columns that they need for reporting. So what it created is the issue with dependency with another team. So we have this data platform team, which kind of helped with this migration, set up Databricks, tables, and we kind of stopped that from migration by not being able to deliver this data. And overall, like it was part of the huge project from migrating tables from Impala to Databricks, which also kind of slowed them down, that they don't have the speed and the users are not able to build reporting on that and basically check that it works well. And yeah, unhappy users, because they can have these columns, they also kind of slow down this whole process, so everyone's unhappy in the end. So we have the pipeline, like what causes the issue is the main part of the pipeline is log level data. So that's the data that is delivered kind of every millisecond. That's why log level data. And the data basically describes user events. So it's clicks, conversions, video events, and yeah, clicks, conversions, impressions, and video events. So that's like typical advertising data in a way that we want to see if the users kind of clicked on the ad, if conversion happened or not. And that's like low-level data. What we go where we go from there is basically we ingest this data, we build mapper part where we choose only specific amount of columns that we are interested in, because log-level data has like maybe 100 columns for the source feed. And then we kind of enrich the data from the database, do the transformations that we're interested in, and calculate the data costs. So the data costs are calculated in such a way that we need to map whether the users that we initially kind of targeted actually watch the ad. So kind of a merge between the users that we have in the system and the users that actually kind of converted, as we call it. So the actual pipeline looks like this. We have Smart Job, which moves files from Google Cloud to Amazon S3 with proper partitioning. And we have this huge kind of data cost attribution job, which pushes the data to HDFS and then to Empower kind of older pipeline. And we want to switch to pushing the data to Databricks. So there are kind of two places where we can add those missing columns. First of those is basically the end of the pipeline with HDFS. And the second one is after data extraction. So what we had at that moment is basically the data was available for the users only on the last step. So it's kind of against this data mesh idea that they have the access only to silver or gold level data, but not to bronze level data, and they were interested in seeing like specific row reports. And we realized that it's kind of much easier if we're going to just provide them this access to this data by building an additional step in the pipeline instead of dragging all of those columns through this huge job, which processes kind of terabytes of data. And it's much harder to process. To add new columns is just data costs and overload, and we don't know whether it's going to kind of shoot us in the leg in a way. So what we did is we actually provided them access to this row feed, and we figured out in the process that we don't actually show them all of the columns because of this mapping kind of modules that we have, because they were interested only in specific amount of columns, and we told them, well, actually we have 82 columns in the source instead of 26, and maybe you want to see all of them instead of kind of asking us each time to add new and new columns. So kind of the logical step there was to just expose this data on that level and have the transformation job separately, which uses only necessary columns and basically doesn't need to process all of this data. So the solution was basically to kind of write the data by event date, event hour, like typical partitioning. And it looks simple, like nothing more heavy than that. We just have one more job in the pipeline that just drops the data by partitioning, and then we get this data in attribution job and do everything that we need after that. So what happened is that the solution didn't really work, and because of the nature of the data. So different data providers supply log-level data in different ways. Some of them just drop it in one file. Some of them drop it in different files. So in this case, we had separate files for clicks, views, and activities. And therefore, as soon as we just kind of do this partitioning and check what was the last date that we processed, we just grab whatever the latest data, which is in that case was clicks. So what we noticed after multiple runs of the jobs, we don't have all of the view of the events. We just have the most recent ones. And it could be clicks or views. But in reality, we want to have like everything over that period of time. So that's why we did a simple thing. We kind of looked into this nature of the data and understood that it's better to deliver it separately in a way. In the data source itself, most of the events are actually impressions, because that's kind of basically what users do. And we have less of clicks, but they always happen after impressions, and conversions also happen after clicks, and we have even kind of less of those. So it's a bit easier to process these different parts of the feeds. So the solution is quite simple, just to deliver them separately, and actually it worked out well for the users, because then we figured out that they actually okay with using it separately, and we've been doing it for a while, like with huge file and huge report. And for them, it actually works much better to have it in separate tables, and then compare, if necessary, different types of events, but usually they still do reporting on the specific type of event. So yeah, it worked out well, and just to share kind of conclusions from there and what you can learn from that. First of all is prevention mechanisms. So it's one thing to kind of draw conclusions and figure out that this is something that we could do better, but another thing is to actually kind of set up some changes within the teams and within the stakeholders communication to basically prevent anything like that happening in the future. So first of all is kind of setting up clear expectations with stakeholders. It happens very different with different teams. Some of them have direct link to the stakeholders, some of them do not. And actually it's very important to understand who's using the data and why they do that. And it helps to kind of provide the data in a better way and more performant way. Another one is that observability is the key. So after that, we started to kind of work on the monitoring system, which didn't catch some of the issues that we had. We had alerts via Prometheus and Grafana dashboards to catch some changes in the source data, but the pipelines were built very differently, and that's why some of them needed new approaches. Another thing that we started to look into is kind of dashboards in Databricks as well, because it's kind of direct link there. So we just wanted to understand the full picture, what's happening. And another one is kind of around the story of divide and conquer. It's always better to design the pipelines initially to scale or to be able to distribute the data transformation load. So we had to do it on the go, but having used this approach, basically we can just use it for other cases as well and fix those issues in the future. And another one is kind of planning major changes carefully. I think we learned that one very well, and now with any changes that are happening, like transitioning to different databases, changing some architecture, we're just trying to plan it as much as possible, especially with dependencies with different teams, which could be kind of hard in terms of actually writing some huge doc with steps, but it works much better than having some stuff just happening in the middle of the quarter when we already have some things to do during that period of time. So overall conclusions is that data setup could be always challenging because having diverse data sources, having diverse data pipelines and frameworks creates different kinds of issues, and we can have some standards or approaches to fix those issues, but overall it's still kind of a changing environment over time. Some errors can be prevented with some of the prevention mechanisms that I mentioned. So basically kind of better communication, better structure and planning. That's the main kind of rules. I think that there are multiple approaches to solving the same business domain issue or technical issue, and so the ones that I presented are kind of not necessarily a golden standard. It's just an example on how what worked well for my team. But overall, you can do anything in terms of frameworks and approaches, but just I think learning as well what's happening with other teams and companies is helpful in itself. And yeah, data evolution is overall hard because especially if you have lots of historical data and different data sources, you'll need to kind of combine a lot of different things and understand the new layout. So it's definitely going to take some time. So thank you for your attention. My contact info, Twitter, GitHub, LinkedIn, and SpeakerDeck. Also have a Scala course on many platforms, so if you know someone who's starting out in Scala, you can recommend them this course. And also I'm Ukrainian, just arrived months ago from Ukraine, so if you kind of want to support some charities, here's the link as well, so thank you. Thank you for your attention.